Hello and welcome. Today we are diving deep into one of the most incredible technologies out there right now, machine learning. We're going to pull back the curtain and really demystify how computers are learning to think, to see, and even to predict. So let's just jump right in. So it really all starts with a simple question, right? You and I, we look at this picture and we instantly know it's a cat. No problem. But how does a machine, a pile of circuits and code, arrive at the exact same conclusion? It's not magic, I promise you. It's actually a really fascinating process of learning from examples. And this idea isn't even new. Way back in 1959, an AI pioneer named Arthur Samuel gave us this classic definition. And the key phrase here, the one you really got to remember, is without being explicitly programmed. So instead of a human writing millions of lines of code like, if it has pointy ears and whiskers and a tail, then it's a cat, we teach the computer how to learn for itself.
Okay, so to really get our heads around this, here is what we're going to do. We'll start with the big idea behind machine learning, then we'll use a cool analogy about how a child learns. We'll talk about the absolute most crucial ingredient, which is training data. We'll even explore what happens when there's no teacher around. And finally, we'll see how all of this stuff is already showing up in your day-to-day life.
So first up, what is the big idea here? Well, at its core, machine learning is all about using special algorithms to find patterns in just massive amounts of data. The machine learns from all those patterns to make decisions or predictions about new stuff it's never seen before.
And conceptually, the whole process kind of looks like this. You take a whole bunch of training data, and you feed it into a machine learning algorithm, which, you could think of it like a recipe for learning. That algorithm chews on the data and spits out a logical model. That model is basically a digital brain that's been built for one specific task. That's the final output, and now it's ready to make predictions.
To really understand how this works, I think the best analogy is to think about how a little kid learns. Let's pretend we're trying to teach a computer to identify a leopard. It's actually surprisingly similar to how you probably first learned what a leopard was.
Because honestly, whether you're talking about a human brain or a complex neural network, learning is fundamentally about one thing: finding patterns. A dog has floppy ears and a tail, a cat has whiskers, clouds have certain shapes. That's how AI gets smart, by seeing these patterns over and over and over again.
Now, the most common way we teach an AI is through a method called supervised learning. This is exactly what it sounds like. We act as the supervisor or the teacher. We give the computer a huge data set where every single example has been labeled with the correct answer by a human. So let's walk through the process with our leopard example. First, the AI is shown a photo that a human has already tagged or labeled as leopard. The system starts to pick out key features: the black spots, the yellow eyes, the rounded ears. Then, and this is the critical part, it starts to assign importance, or what we call weights, to these features. Finally, it builds an internal, general idea, the model, of what makes a leopard a leopard. Okay, now here is where it gets really cool, and this is how it connects to the tech. When you hear people talk about neural networks, this is conceptually what's going on inside. They're made of these hidden layers of computation. So just imagine, that first layer might just be identifying basic things from the pixels, like shapes and colors. The next layer over might learn to see those shapes as ears or paws, and then the deeper layers start combining those features to recognize a whole face. It's all working together to build a full picture, just like a kid's brain connecting the dots. And this chart really just nails that concept of weights. The model learns fast that black spots are a huge giveaway for a leopard, right? So that feature gets a high weight, say a 0.7. Yellow eyes, well, they're more common in other animals, so that gets a medium weight. And having 4 legs, that's almost useless for telling animals apart, so that gets a really low weight. The algorithm just keeps adjusting these weights over thousands and thousands of examples until it gets incredibly good at making the right call. Okay, so the algorithm is obviously pretty smart, but it can't learn in a vacuum. It absolutely needs a study guide. And in machine learning, that study guide is its training data. This is, and I'm not exaggerating, probably the most important part of the entire process.
There's this classic saying in computer science, and it has never, ever been more true than it is today with AI. Garbage in, garbage out. It's simple. If you train your model on data that's flawed, or biased, or just plain wrong, you are going to get a flawed, biased, and wrong AI. End of story.
So to put it simply, data is the fuel. Without it, the most sophisticated algorithm on the planet is just an engine that can't start. The model learns everything it will ever know directly from the examples you give it.
So what makes data good data? Well, it really boils down to 3 main things: First, quality. The labels have to be accurate, no mistakes. Second, diversity. You need to show it leopards in trees, in the grass, sleeping, running. You have to cover the whole range of possibilities. And finally, volume. For big, complex tasks, the model needs to see a massive number of examples to get it right.
And if you're wondering why this matters so much, get this. Some stunning research from MIT shows that up to 95%, that is a huge number, 95% of generative AI projects fail to ever move past the experimental phase. And a massive reason for that, poor data quality. The foundation just isn't strong enough. Wow, that staggering failure rate just goes to show how hard and expensive it is to create good, labeled data. So that brings up a really big question, right? What if there is no teacher? What if your data has no labels at all? This very question leads us to the second major type of machine learning. Because sometimes labeling millions of data points just isn't possible, or maybe you're just exploring. You're trying to find patterns you didn't even know were there to begin with. And this is called unsupervised learning. As you can see, it's pretty much the opposite of what we just talked about. Supervised learning, that uses labeled data to predict an outcome, like answering the question, is this a leopard? Unsupervised learning uses unlabeled data to discover hidden patterns, like answering the question, can you group my customers into similar tribes based on how they shop?
And this is incredibly powerful out in the real world. You see it everywhere. E-commerce sites use it to group customers for product recommendations. Banks use it to spot weird transactions that might be fraud. It's really a tool for pure discovery, for finding structure in a giant sea of messy, unorganized data.
Which brings us to our final section. You know, this stuff isn't just theory, and it's not just happening in some lab somewhere. Machine learning is already deeply woven into the world all around you, often in ways you probably don't even notice. Think about it. When your map app perfectly predicts traffic on your way to work, that's machine learning. When you're shopping online and a store recommends a product you actually like, yep, that's ML. And that spam filter that keeps your inbox from being a total disaster, that's one of the oldest and most successful examples of machine learning in action.
But of course, with a technology this powerful, there are some pretty big challenges we have to keep in mind. For one, some of these models get so complicated they become a black box. They give you the right answer, but it's really hard to trace back exactly how they got there. And then there's the huge ongoing risk of bias. Remember, a model only knows what we show it. So if it learns from data that contains our own human biases, the model can end up just repeating or even amplifying those biases in its own decisions.
So here's the crucial point, the main takeaway. We are no longer just programming machines, we are teaching them. And that leaves us with a really profound question to think about. As these machines get better and better at learning from us, what are the things we should be the most careful to teach them?